All right, so do you guys want to talk about that daily problem that you had or not really? You feel like you can do it?
You want to go
Can we
over it?
Sure. Sure. Yeah, let's see. Are we hooked up? There we go. Okay, so I tasked you guys with looking at a 1D fluorine chain, right? So this was number 15?
Yes.
Nope.
1D fluorine. Okay, so how did you guys even start this one?
By the electron configuration.
Yep, so electron configuration for fluorine. What was it?
1s2, 2s2, 2p5, I think.
Yep, you're right. Okay, so now we have our band structure. We're going to have our fluorine atoms like this. And we're going to have our unit cell where there's one fluorine atom per unit cell. We're going to go to plot that. What do we have on our x-axis down here?
K.
Yep. What else?
0 to pi a.
Yep, pi over a. And then we got e. Yep. All right, what'd you do next?
Okay, so since you wanted us to write out the orbitals and the block functions for 0 and pi over a, I kind of did that to the side.
Yeah, so you looked at 0 and pi over a for each of the orbitals, right?
Yeah.
Okay, so let's do that. We're going to have the 1s and psi 2s. They're going to be the same, right? Like same type of geometry. They're going to be different in energy, but we'll get to that in a minute. So let's look at 0 and pi over a. What does the block function look like at a k
It's
of
all
0?
sigma bonding, so it's just with
Yeah.
chi 0 plus chi 1 chi 2.
Oh, right, like you said, positive, and it's sigma bonds.
Mm-hmm.
3, like that. That looks pretty good, right?
Yeah.
Okay, and then pi over a, that's when they're out of phase. And what's that going to look like?
Colored in every other.
Yep. And what type of interaction is that? Sigma pi delta? Yep,
Sigma star.
Yep. Okay, so now let's draw the dispersion for each of these. We're going to have two of these orbitals. We have the 1s and the 2s, right? And how do they run?
It would be bonding at the top, so it goes bottom, high to low.
Remember, this is at pi of 0, right? Is this low in energy or high in energy?
Low.
Low, yep. So we're going to start low and run high.
Completely wrong. Nice.
No, you got it right.
Yeah, you just said it the opposite way.
I did everything bad.
There we go. There's the 2s. Okay, now we have to worry about those pesky p orbitals, so let's get there.
Oh, that was only the s's?
That's only the s's.
I did that part then.
That's okay, that's why we're covering it. It's better to get it wrong here than on the exam. So.
What about both?
No. I get it right on the exam, I have faith. Okay, so same thing, px, we're gonna say this way is our x direction. So what's the block function gonna look like for the px if it's in a line?
There's like sigma anti-bonding, so they're parallel to each other, yeah.
So like that, and then you're saying anti-bonding, so is this good?
Yeah.
Yep. So this is a sigma, why is it sigma? Why is it a sigma star? What tells you that this is sigma?
Because there's one region of overlap.
Yep, overlap in one region. What were you gonna say, Maddie?
Nothing, right? Never mind.
You could do, no, what were you gonna
No,
say?
I realized what I said was wrong. I said out of phase, but it's not.
No, they're out of phase with one another. Yeah, you're right.
What? I
So-
thought that's in phase because it's
Or
like.
excuse me, they have destructive interference.
Okay.
So these ones are the ones that are going to be out of phase. And what type of overlap are they going to have?
Constructive.
Yep, constructive, so sigma. There we go. Okay. We have to worry about the other p orbitals. We have py and pz. They're going to look the same. They're degenerate. One's just coming out towards us and one's going up and down. So let's plot what those functions are going to look like. Okay, now we need to color them in for the sign of each atomic orbital. If we color in like this to start, what's the next orbital going to look like at pi, or excuse me, at k is equal to 0?
It's gonna be the same thing repeated.
Yeah. Yep, you're right, Tara, bottom. Josh, what about this one?
It's every other, so the shaded goes on top.
Yeah. Okay, John, can you tell me what type of interaction this is going to be?
Bonding.
Yep, it's bonding, and what type of bonding?
Pi.
Okay. Maddie, what about this guy?
It would be anti-bonding, so pi star.
Yep, perfect.
Thanks for the assist, John.
Now, which
What
one?
was that?
Thanks for the assist. You set me up and I dunked it.
Teamwork makes the dream work, man. Now, can anyone tell me which one's going to have a greater amount of dispersion, or which one is the bonding and anti-bonding is going to be a greater energetic difference? Is it going to be the px, or is it going to be the py and the pz? So which one's going to spread out more?
Px.
Pi and PZ.
It's actually the px, because remember, it's sigma type overlap. These guys have pi.
So yeah, it's better quality.
Yep, better quality. So we're going to run up here.
I did that wrong then.
That's okay. That's why we're doing it. I need to zoom out a little bit.
Hey, John, we still love you.
So we need to draw the px. It has sigma type overlap to start with, so it's going to start low in energy, and it's going to move up. So that's the px. What about the py and the pz? How's that going to look?
It's the opposite, but more close together.
Yep. So less dispersed, closer together. So that's the px and the py. Or excuse me, pz and py. Okay. So how many electrons does each band hold again?
2.
2. So where do you suggest we fill in? Like where's our Fermi level going to be?
I think it's between.
So it's near the top. It's almost right at the top.
Yeah, it's going to be somewhere right along here. Because this px, since its dispersion is so great, there should be only one electron in that px. Or excuse me, geez, px. Said px. If you think about the atomic orbitals, you have a system that looks like this, right? For fluorine. So these two are translatable. Does that make sense? Are there any questions about that one?
I don't
I thought
understand.
that for PX, the anti-bonding was at 0. If we look back at the...
Oh, yeah, it is. Geez, we screwed that up. My bad. Other way around. We'll redraw that. Sorry. We'll do it a little bit smaller, too.
Yeah.
Good catch. That could have been catastrophic. Well, it was catastrophic. All right, yeah, like Morgan was saying, these should go the other way around. That's the PX, this is the PY, PZ, and then we'll have the Fermi level right about here. Oops, except I need to make this. There we go. Good catch, my bad. Tara, you looked like you were getting pretty frustrated. Was that your question?
I don't understand how you're getting the Fermi level.
So how do you know where the Fermi level is?
Mm-hmm.
So you have to know how many electrons you have in your system. So how many total electrons do we
We
have?
have 9 and we could have 10.
Yep, we have 9 electrons, right?
Yeah.
Because we're talking about fluorine. So this guy holds 2, this guy holds 2, so we're at 4. These both, there are 2 that are on top of one another. So that's 6 and that's 8. And since this guy stretches really high, this one's gonna be partially occupied. So just like we had with our molecular system, where this is our 1s, 2s, and then the 2 p's. So on. Each of these, we'll say this one's the PY, this one's the PZ, and this one's the PX. They get split a little bit, so these energy levels change a little bit as the fluorines get closer to one another too. So, uh-oh, my internet connection is unstable, it's saying. No, we're back. Okay, did that help, Tara, or no?
Yeah.
Okay. Any other questions? Good catch on the way that was meant to run, my bad. Okay, so now let's go a little bit further. Last time we were talking about DOS. We're gonna move to something called PDOS in a minute, but we need to talk about having more than one atom in a unit cell before we get there. So more than one atom. And remember, what did we say about the number of bands? What's that equal to?
Number of electrons.
Not number of electrons exactly.
Number of orbitals.
Number of atomic orbitals, yep. In the unit cell. Okay, so now what we're going to do is we're going to start with that 1D hydrogen chain, but we're going to include 2 atoms. So let's consider a 1DH chain with 2 H atoms in our unit cell. Okay, last time we would go from point to point like that, and we would say that there was A in there. This time we're going to go from here to here, and we're going to say that's 2 times the distance 2A. Okay. So let's start looking at our block functions. Our block functions. So we have at the gamma point, and do you remember what the value of K was at the gamma point or the hangman?
It was 0, 0.
Yep, 0, 0. We're going to keep with 0 since we only have one direction. Okay, and then we'll have at K is equal to pi over A. Okay, now we have to consider what's going to happen at these points. At k is equal to 0, we have two options. We've got where there's a node that way, or there's another option. And remember, the node is along here. So since we have two atomic orbitals in here, and we're looking at some sign changes, our band structure's got to look this way. It has these two options. So if you notice, this would be like chi 0, this is chi 1, this is chi 2. And there's still a plus sign between each of these. Now, why are we considering the system that's in phase and also the one that's out of phase? What makes it different from just our regular old 1D hydrogen chain?
You're considering it as a full group. It's not
Yeah.
actually changing as you go past the unit cell.
Right. So if you're thinking about symmetries, you're thinking about the number of points at that gamma point. There has to be two because we have two atomic orbitals. Okay. At pi over a, what's that going to look like? We'll mark our unit cell again. Oops. Yeah. We know our block functions, they have to be out of phase with one, out of phase with one another. There's a sign change. Okay, so what did it look like at pi over a for the 1D system, where we just had a single hydrogen atom in the unit cell?
Every other was colored in.
Yep, so we're gonna have that one still. Oh, except that matches that one, my bad, we're not gonna have that. I'll redraw that. So that's not our option because we're just matching that, guys. We got to do a different one. So could you think of any other ways to fill these guys in where they're out of phase with one another?
Is it every other node is colored in?
Yep, like this. Okay. So that one we're moving it in and out of phase. What about this guy? What could we do to have one sort of like this? We're gonna
The
start
first one's colored in,
Mhm.
yeah, or that, and then yeah.
Yeah. Just like that. Okay, so now let's talk about what type of interactions these are. This very top one. Bonding, anti-bonding across the,
Bonding.
yeah, bonding, yep. And what type of overlap is it?
Constructive.
Yep, constructive. And overlap in how many regions?
Sigma.
All
Yep, sigma. This guy?
Still
Yep, still sigma. What type of interaction between these guys?
Anti-bonding, so sigma star.
Yeah. This one.
sigma.
Mhm.
No.
Sigma star.
Sigma, yeah, but it's kind of, there's a bonding interaction here and a bonding interaction here, right?
Yeah. Well, I mean, are we looking at between from cell to cell, the bonds between those, not necessarily.
Yeah,
the bonds.
cell to cell. So cell to cell, it's anti-bonding, right? But
Mhm.
sigma in cell. What about for this guy?
Same.
Sigma, but sigma star inside.
Yep. So let's try to plot these things out. Am I okay to move this up?
Yeah.
So now our band structure. We're going to have the same K value, 0 pi over A. I'm going to keep track of energy. How many bands do we have to draw, keeping in mind how many atomic orbitals we have?
2.
2. Okay, let's put in some points first. Looking back at what we saw for the gamma point, which of these orbitals or the crystal orbitals that we drew, which one is the highest in energy and which one's the lowest in energy? So could you tell me which of these is the most energetically favorable?
Probably the very first one.
Yep, that very first one, that's definitely the most energetically favorable. So we're going to go down here. We're going to put a little point there for it. Which one is the least favorable?
I think the third one.
Third one. This one's not great,
The
but is it? It's still got some type of bonding interaction, right?
Would it be the second one because it's all anti-bonding?
Yep. So now these two, are they actually any energetically? Are they energetically different from one another?
No.
No, they're not. They're the same. So where do they rank in terms of their energy?
I think the fourth one would be higher in energy than the third one.
These two are actually the same right now. But you're right. Once we'll talk about why you're right in a minute in a realistic system, Tara. But what about so these two we're gonna say are degenerate right now. How do they rank compared to these guys?
Oh, it'll be like in between them.
Yeah, in the middle.
Yeah, so there's an in-between point. So the way the band structure looks, it's like we take our original 1D structure and we fold it in on itself. So it looks like that. Okay. So Tara said that this one is higher in energy than this guy, right? And in a realistic system, she's exactly correct. We're going to talk about why she's correct. Am I okay to move this?
Yep.
So what if we tried to make this one-dimensional hydrogen chain, what would happen to it? Like, could we make this at standard temperature and pressure?
No.
Okay, everyone's shaking their head no. Why no?
Turns into H2.
Yeah, breaks apart into H2. It'll fall apart. That's more stable for it. So let's talk about how we would know it would fall apart into H2. To do that, we're going to talk about Jahn-Teller distortions. Or physicists, they call these Pyrrhus distortions. Which I think I misspelled Pyrrhus, so don't quote me on it. And what happens in a Jahn-Teller distortion is any nonlinear molecule with a spatially degenerates, electronic ground state, will undergo a geometric distortion that removes the degeneracy. Let's translate this into usable English. Okay, so as an example, we're going to look at cyclobutadiene. Okay. And we're only going to consider the pi orbitals. We're going to look at the Huckel pi MOs. So does anybody know what the skeletal structure of cyclobutadiene looks like? So first word cyclo, what's that tell you?
The ring.
Ring, buta?
It's a
Four.
5-carbon ring with two
with two
um,
double bonds.
on a 1 and 3 position, and then it's typically charged.
Box.
There's
Or
box.
do you not even know those two words?
Sorry, wait, no, that's right, Matt. You're the
Yep.
organ.
Cyclo ring,
That's just
buta,
another
4, diene, two double bonds somewhere in there. And John, you're right. Normally this thing is charged, but right now it isn't. Okay, let's draw out the pi MOs for this system. So what we're going to do, we're going to be looking down on the PZ orbitals that are sticking up. So I'm going to try and draw a side view of this thing, which sucks. But we're going to be looking down on it. There's our eyeball. We're going to be looking down on it that way. All right. So the cool thing about Huckel diagrams is if you take a ring-like structure and you turn it on a point. So we move it like this. That actually shows you what the molecular orbital diagram will look like, or the Huckel diagram will look like. For each point that you actually have an energy level. So if we go to draw out that MO diagram, that's what it's going to look like. Okay, let's try to draw what these orbitals look like, though. Remember, we're looking down, so all we're going to see is the top of these PZ orbitals. So looking at this one, again, we're looking down. These are the tops of our PZ orbitals. Should they all be in phase, out of phase? How should they look? Or is this fine?
I think that's fine.
It would be
Yeah, that's
in.
good. This is completely bonding. They're happy. What about? So we're moving up in energy, which means we're introducing a node somewhere. What's this one going to look like?
Pi star.
Yeah, it is a pi star.
Maddie's on top of our pyramid today.
So it's out of phase across this way. What about this guy? It has to be degenerate, remember, meaning they're the same energy. How's this one going to look?
Just flat. So through row. Horizontal. Horizontal, I should say. Is that?
Horizontal. So you're saying across this way?
Not horizontal.
Like a corn cob.
Oh, this way.
Corn cob.
Yeah.
Corn cob. So we got corn cob. What's this way's corn cob? What's this way? I don't know.
Popsicle.
That's a ladder.
Popsicle.
Corn cob, popsicle.
Fucking
Makes me really want to go outside and grill.
We really eat everything to food.
Yeah, this is the worst class because it's always right before lunch too, and I'm like, oh, I just want to eat. All right. So what do we got? What do we got for this top one?
Diagonal.
Like that. Okay, now we got to fill in electrons. We'll use red because I have it here. How many pi electrons does this system have?
2. Oh.
Yep, 4. Each of these bonds contains 2. It has two pi bonds. We got 1, 2, 3, 4. This is a diradical system. Is this stable?
No.
No. That's why it's really, I mean, you can go and you can find types of cyclobutadiene out there, but generally it's difficult to find and difficult to make. So what's going to happen here? So this is going to undergo a Jan-Teller distortion.
Of course.
Yeah. Okay, so originally we had our box. We have C1, C2, C3, and C4, let's say. What do we know about all the bonds in here? If we're going off of this system.
Oh, like the angle?
Or I'm talking about like, oh yeah, okay, angle. Well, no, we won't worry about angle. What's the, like, so is this C1, C2 distance different than the C2, C4 distance?
No, they're all
They're all the same. They all have a double bond and a single bond.
It's technically aromatic, so.
Yep, it's technically aromatic. So all these bonds should be the same. C2, C4, C4, C3. What did we forget? C3, C1. So all those should be the same. And that should be a square. But what actually happens is the system distorts.
So now it's a rectangle.
Now it's meant to be a rectangle. So these two are equivalent. And these two are equivalent. Whereas originally,
Geometry.
oh yeah, taking you back, man. So in this case, what? Distance of C1 and C2 does not equal distance of C2, C4. Now, how does this influence the electronic structure? So if we look back at our MO diagrams, this bond is getting stretched out, right? So we got this system. So we're going to ask the question, which is lower in energy? So we got these two systems.
Probably the first one.
So you're saying this one's the lowest? Why do you think that, John?
Because the bonding interactions are closer together.
Exactly. Whereas with this one, what were you going to say?
They're just getting farther apart, so you're going to have more anti-bonding character.
Right.
Or
And in that
non-bonding.
short distance, this is anti-bonding. So this one's lower in E. This one's higher in energy. So now, how is that going to change our MO diagram?
It would have the one thing be higher than the other.
Right. So it's going to distort. What's going to happen is this one is going to get lower in energy. This one's going to get a bit higher in energy. And they distort this way. Let's call these, we're going to label these guys with phi. And we'll do the same up here. So that way we can compare them. Now, what's going to happen to the filling here? Tell me what's going to happen with those electrons.
There would be 2 in both phi 1 and phi 2.
Yep. And now this guy is empty. Have you guys ever talked about Jahn-Teller distortions at all, or no?
Nope.
Okay.
Never.
Okay, so that's what happens. Nature does this to stabilize the system. It'll force the bonds to elongate a little bit, so that way it's energetically more favorable, and you move from a paramagnetic system, one with unpaired electron density up there, to a diamagnetic system, where all the electron density is paired up. Okay, does that make sense? Okay, so now let's go back to our 1D hydrogen chain. So we know our 1D hydrogen chain does not exist at room temperature and pressure. At really high pressures, we can get this to exist. And we said what happens to it? It breaks into H2, I think, right? So let's draw out what's going to happen. Originally, we said all of these, they have a distance of A apart. Tell me what's going to happen in this picture. So let's call this one, I don't know, distance 1, this one distance 2, and distance 3.
So distance 2 is going to be smaller.
Great.
So distance 1 is going to shrink. What's going to happen? They're going to all just keep shrinking, right?
Mm.
Oh, wait, no, I drew that wrong. Whoop.
Hmm.
These two are going to shrink. What's going to happen to this one?
It would break.
Yep, it's going to break. It's going to grow out. And what's going to happen after the distortion? We're going to get a system that looks like this. So Jahn-Teller, we have that Jahn-Teller distortion, and it's going to break these apart. It's going to make them no longer equivalent. Let's see what impact that has on the band structure. Am I okay to move this up?
Yep.
So Jahn-Teller distortions or Pyrell's distortions. In solids. So the first thing is no system wants to be metallic unless it absolutely has to be. No system will be metallic if it can help it. So solids also undergo Jahn-Teller distortions. Jeez. I'll try that again. They undergo distortions, and it often makes a band gap. Opens, band gap. So if we go back to more of our primitive drawings where we have a band structure like this is before. A Jan Teller distortion. It distorts. Forgot EF. And now there's a band gap here. So when the valence and the conduction band no longer touch, that's called a band gap. So let's hop back to our two-dimensional system. We drew our band structure. And let's see what happens as we let this system distort. Am I okay to move this up?
Yeah.
So what happens to the band structure? Of our 1D H chain. So we're going to have before. We'll plot out that band structure. We'll have after. Except I need to move up a little bit. Okay, what's our x-axis again?
Okay.
Yep, okay. 0 to what?
Power.
Yeah. And we got E.
Oh, what's the question again?
So we want to know what happens to our band structure of the 1D hydrogen chain if we allow it to go through a Jan Teller distortion.
Okay.
We're going to draw, oops, what it looks like before. There's an E on the end of before, right?
Yeah. Yes.
Sounds right.
So we already drew this. What's it look like again?
Just a single or two.
It's just a
are we
single
talking about
S
just the
orbital.
how big's our A?
Like
Is
that,
it
right?
including 2 right now, or is it just?
Yeah.
It's including 2 right now.
Okay.
So this is before. We're going to let it distort. And what's going to happen? We're actually, in our system, where's our Fermi level? We never indicated that.
In the middle.
Yep, right in the middle.
Wasn't this for a H chain that's 2? It's
Yes.
a 2.
Yep, we're talking about this one. Where that's our unit cell. So we shouldn't be going to pi over A. What should we be going to?
2A. Oh, pi over 2A.
Yep, 2A. And actually, we should probably change that in our other ones. So what we drew here should actually be pi over 2A. So back to the system, we know this is where our Fermi level is. What's going to happen to the band structure? Teller.
The Fermi level would stay the same,
Mm-hmm.
but the bands would stop touching.
Right. So EF will be right in the middle, but now the bands are going to they're going to split apart a little bit more.
It's delicious.
Okay. Now, why why is this one going lower? Why is this one going higher? And this has to deal with what Taro was saying. So we're gonna look at these points here and here. Okay, so we're looking at pi over A. These things are going to Jan-Teller distort, and we said these ones are going to move closer like that, right? Which one's lower in energy then, the top one or the bottom one?
The top one.
Yep, the top one, because they're bonding in that unit cell. This one, they are still going to move closer this way, but they're anti-bonding across there. So this gap opens up. And this is where that's going on, and this is where that's going on. Okay. We're going to see Jan-Teller distortions pop up again once we start talking about octahedral complexes, but I just wanted to give you an idea. All right. Let's talk about what happens to the density of states. So am I okay to move this away?
Yeah, you're good.
Okay. So what happens to the DOS? So let's draw that band structure one more time. In this case, it is distorted. And again, we have our Fermi level. All right, now we're going to plot the density of states. We have our energy on our y-axis still, and we have density of states on the bottom. Our Fermi level is going to be the same. But what does our DOS look like? How did we define density of states again? It was equal to some differential. Oops.
dn over de.
Yep. And what's n?
Number of states.
Yep, number of states. And DE is just an energy interval, right? Okay, so there's a large number of states here in a small window of energy. What's that going to look like in this plot?
Is it going to be a straight line?
Yep, we're going to get a straight line here. What about at the top here?
Another straight.
Yep, another straight line. And since there are a handful of states in between, we get something that looks like that. What's the top one going to look like? That top band.
I'm guessing the same, but
Yep. Yep, it's going to look exactly the same. Just not colored in. So remember, these are the occupied states. They're more bonding in character. These guys are the unoccupied states. They're more anti-bonding in character. Okay? Does that make sense? Okay, cool.
Can you go back to the change in band structure, the diagram that you just did? I wasn't sure what the H, so the diagram we did before this.
Okay, so this guy?
Yes. Okay, so I was just looking that after the distortion, so it just shows that the H2 is broken off into two separate. Is that what that's showing? That you're going from the hydrogen chain to it being broken off? Is that what?
Yes, or at
Okay.
least not completely broken up, but the bond between, like, let's say hydrogen 2 and hydrogen 3 is becoming weaker. Whereas
that
this distance is getting shorter.
is that bond completely gone on the top band then?
No, it is not completely gone.
Okay.
So these guys are still in a unit cell. We haven't let them escape completely. Let's pretend they're under some sort of, like, under some pressure.
Okay. All
Okay.
right, sounds good.
All right. We've kind of circumvented what the Fermi level is. Let's talk about what is the Fermi level. So what is the Fermi level? Morgan, you around?
Yep, still here.
Cool. Are you past your synopsis or no?
No, I'm a first year student. We won't do that till end of second year.
Okay, this is a question I got, so I'm going to ask it to you. Do you know what the definition of the Fermi level is?
The definition of the Fermi level. Isn't it what? Okay, so the energy that the Fermi level is at is when you're below that, your electron is unable to travel freely. When you're above that, your electron is able to travel freely and conduct.
Yep, that is true, but that's not the formal IUPAC definition. Yeah, it's hey, they'll ask you that sort of stuff.
Do you want me to
Well-
struggle for another 15 minutes trying to answer it?
Yeah.
That's the
Yeah,
sarcastic
to.
answer.
It would be helpful if you'd be up at the board and sweating it out and go, that's a really good question, and then talk about something else. So I had this question, and what it is it's defined as the zero of chemical potential.
This poor guy's never coming back.
I know.
Leaves chat right.
Hey, what
You're
was
really gonna call me
the
out like
symbol
that?
for chemical potential back in PChem 1?
Oh, I know that one.
All right, yeah, go for it.
Yeah, that's mu.
Yeah, exactly. So it's the zero of chemical potential at 0K. Thermodynamically, it makes sense. Intuitively, no one would probably guess that. Or what you did say, where every state below it, electrons are free to move about. They're all populated there. Above it, it's unoccupied. So every state above level is unoccupied, and below is occupied. It's also defined as having a Fermi Dirac. Also, so speaking of Dirac, if you're really bored, sometime watch the Dirac lectures. They're actually pretty entertaining. Distribution of having an occupied.
What is that one after Fermi?
Which one?
After Fermi? Fermi.
Dirac. It's named after Paul Dirac. Occupied level 50% of the time. So it follows this mathematical formula where the probability of that energy comes from also statistical mechanics is 1 over E minus EF, so whatever energy we're talking about, divided by KT plus 1. And that should equal 1/2. Not that you might run into that too frequently, but just in case it's around, it's around. Okay.
Next test, guys.
Yeah, get ready.
Yeah.
Oh, I got a good multiple choice question.
Oh, God.
You can keep that one.
Here we go. Is that KT? Or,
That is KT, yep, where that's the Boltzmann constant.
oh, okay.
And T is just temperature, whatever temp we're talking about. Okay. I'm going to move this around. So the density is states, all they can really tell us right now is something or is something not a conductor. Basically, if there are some densities of states touching the Fermi level, we have a conductor. If they're not, they have some insulating properties or they're a semiconductor. Not really a lot of info. However, what we can look at are something called the projected densities of states. Or PDOS. And like we said, the DOS is not really descriptive. And it doesn't really tell us important chemical information, not a lot of it. But if we could look at contributions, we could tease out contributions of different atoms. In relation to the total DOS. We might get some more chemically intuitive or build a better chemical understanding of what's happening. Might be able to have a better idea. Chemical understanding.
Does that say if we could tease out?
Yep, if we could tease out those contributions.
Nice
We
try.
might.
Oh,
I was
right.
just making sure. I don't think I've ever teasing with like.
You never teased out something? You got to go lobster diving sometime. That's when you tease them. You poke them in the back, you tease them out,
Yes.
and then you have a delicious meal. It's awesome. Chemical understanding of our system. Okay. I'm going to move this up a little bit. Okay. So the question becomes, how can we partition the DOS? And to do that, let's look at a simple diatomic molecule. So consider a simple diatomic molecule. We're going to look, I don't know, we'll pretend it's like HF or HCl. Something like that. So remember from the linear combination of atomic orbitals, the LCAO, we have a wave function and this junk. Can you guys tell me what any of this means.
Well, the wave function of this diatomic molecule
Yep, so that's our wave function.
is equivalent to.
Mhm.
We wrote this out before. I should know this.
Yeah, you're getting there. So what are
We got the wave
C's?
function down. That's a good start. Pecan,
What are C's always? Or
isn't that the
K?
contribution?
Constants.
Yep, this is
Constant.
contribution,
All right.
which is a constant, of atom 1 to psi. This one's the contribution of atom 2 to psi. What about these guys?
Distance.
Isn't that? You
What
say
is it?
something, Matt?
Ah. I thought Maddie had
Oh,
an
it's,
idea.
I said it was the
Um,
distance between atoms.
I'm sorry, you cut out for a second. What'd you say?
Bond length.
Nope, not bond length.
Whatever.
This is the contribution of atom 1.
Density.
Not density.
isn't that like their
Mhm. These are like the atomic orbital contributions. We can be a little more formal and say these are the basis functions. On atom 1. These are the basis functions on atom 2. But we remember those can be thought of sort of similar to the atomic orbitals of the system. Okay. And remember we said that this is the LCAO. What does this stand for again? L.
Low.
Nope. Linear. What does AO stand for? You know that one.
atomic orbital?
Yeah, there we go.
Woo!
So linear, something with a C, atomic orbitals.
Chicken.
Chicken's
There we go.
delicious.
Linear
Better-
chickens.
better guess
Oh
than
no,
we're
we
gonna come
we
with.
don't have good times with chickens here. That's point
Yeah.
groups.
Combination. But if we were trying to draw a linear combination or linear chicken atomic orbitals, I don't know. Let's see. I want to draw a chicken really bad now.
Me too.
There we
These
go.
drawings. There we go.
That reminds me of that chicken that you gave us for that quiz on point groups.
Yeah, that's exactly what I'm thinking of. And we
Uh-huh.
said the chicken's linear, but you're like,
Chicken.
no.
But really, is it though?
It
So-
was, wasn't it?
Let's see.
Yeah, we didn't have an infinite axis technically, so we
Oh,
all got it
geez.
wrong.
This one's
Is that a chicken too, or is that like
Dinosaur. It's Charmander. I don't know.
Yeah,
Dinosaur chicken.
that's all chickens are. They're just dinosaurs, man.
Technically.
Definitely could have been a Charmander. Yeah.
Now we got that. Those are our two options. We either have red chicken or white chicken.
The one on the left looks so much better.
Don't worry about him.
I'm body shame.
There we go. Chicken.
Wait, are we supposed to draw this?
No, you don't have to draw that.
This is very important. What are you talking about?
Side chicken.
Oh, we got
Well,
the
this
wave
can be
function of our
drawn.
chicken. We're good.
I don't want to draw it out. I don't know.
This is gonna be the first question on the exam.
What is
What is the wave
chicken?
function of a
What did you think of my chicken? Please read it. Anything below a 7, fail.
Giblet versus chicken.
Yeah.
Who would win?
Yeah, who's gonna?
Probably chicken.
Okay. So we can,
Okay.
so we got our chicken. Back to this guy though. So we can figure out these C values. We can do it from normalization. So if we normalize psi, and what does normalization mean again from PChem?
Making that equal to 1.
Sigma star times sigma d tau is equal to 1.
Okay.
Yeah, there you go. So we do that. We can get C1 and C2. So we can know those. Okay, when we do that, we get 1 integral, whoa, ding.
Now you mute Tara.
Wait, I screwed up my screen and now I can't see what you're writing. I
Oh,
pushed the button.
It's just a little stick figure of you with stink lines.
Oh,
do we need to, do you need me to share it again?
yeah.
Okay. Let's see. Did that make it work?
Thanks. Yeah. Oops.
So we're going to normalize our wave function. That's what we have. What we end up getting is something that looks like this. We get C1 squared plus C2 squared plus 2 C1 C2 S1 2. So these are our coefficients. This is a collection of stuff. This is actually an overlap integral. We haven't gotten to that in PChem yet, but this is something called an overlap. So, and what it is it's like the integral between chi1 and chi2. Okay. So we know that C1 and C sub 2 squared are assigned to chi1 and chi2 respectively. So this one connects with that basis function. This one connects with this basis function. But what the hell does this portion mean?
That's what we were asking.
Yeah. To C1, C2, S1, 2. Okay. So what this is it's looking at the overlap between these two basis functions. And there are multiple ways to divide up, whoa, here we go. Divide up this term. And the reason there are multiple ways to divide up this term, this is where the idea of why is it difficult to say what is the charge on an atom? So this is the difficulty. In determining charge. The concept of charge. So let's look at an example. HCl. Where does the density of the H end, the hydrogen end, and the chlorine begin? So that's what HCl looks like. If we draw its electron density around, look at that, right? So where would you say, where does the density of the hydrogen end and where does the chlorine begin?
More towards the hydrogen because the chlorine is contributing more.
Okay, so you would say like that's the point?
Yeah.
Would it have that bend to it? Like, is it, or is like this better? Or is like that better?
Won't chlorine be bigger because it's
Yeah, so that one's kind of crummy, but what about right in the dead center?
No.
Seems reasonable.
Let's say no. I don't know.
Yeah, I'm not saying no.
Just no.
Just no.
Not answer.
No. Yes and no are always acceptable answers to any question.
No, it's not.
wrong.
Yeah, except when it's not.
I
So-
guess. So in my mind, oh, sorry to cut you off. So in my
No, go
mind,
ahead.
so the orbitals, they don't really end. They kind of just stretch on and on forever to decreasing density.
Right.
So like if you look at it from that point, it's arbitrary.
Yeah.
But if you look at the HCl molecule, it's a polar molecule and it's gonna have a dipole. So the chlorine's gonna have more electron density around it. So
Yeah.
there's like unequal sharing. So
But with these lines I've drawn, which one's right?
So yes.
So yes.
So just
Yes.
maybe all of them. If it's
Yeah,
arbitrary.
all of them. Yeah. Who the hell knows? That's the point.
Okay.
One can draw multiple division lines. And we have a good idea of which one makes more sense. We say probably like either this blue one or this red one make more sense than that dashed line or that red one. But we can't really agree on where it ends and where it begins. So there is no 100% correct answer. And this is actually why charge is a concept, not an observable. We can't get a true value for a charge. We just set an arbitrary amount. So next time, what we're going to do, we're going to incorporate this idea into how we talk about densities of states. But before we do that, for those who are in PChem or those who are computational chemists, so there are multiple ways. Charges are calculated. And that overlap integral that we have, the way are calculated or that are partitioned. So there are Hirschfeld charges. There's the Mulliken charge analysis. You guys don't have to write this down. Especially because you can't see it right now. Does anybody know any other types of charge analyses?
Bader.
Yep, Bader's a big one.
Okay.
There's also Voronoi. Bader tends to be considered the best, which I hate because the guy is totally pompous about it. And he clicks, mine's the best. It's way better than all of these. But they all have their weaknesses and strengths. The biggest problem is sometimes they have conflicting answers. So what do you do then? That's where you try to use your chemical intuition to come up with a good explanation for what's going on. Okay. So next time, what we're going to do, we'll go back to PDOS and we'll talk about how do we partition this, not our chicken. How do we partition this to get more useful information? What contribution does that first atomic orbital have, and which contribution does that second atomic orbital have? But before we go, I'm going to put our chicken back up because I'm pretty proud of that.
Yeah, my chicken's actually turned out worse. I don't know how.
I was going to say this one, I wouldn't eat that one.
That's a McDonald's chicken right there. The other one, that's like a.
It's getting turned to pink slime.
McDonald's is good.
So, are there any questions that you guys have about the material that we covered today?
No.
Okay.